The Near spacecraft even transmitted information back to Earth for about 2 weeks while on the surface.
But it has lost its radio link with the Earth, and so now it's simply sitting there mute for millions of years.
The asteroid explorer Hayabusa of the Japan Aerospace Exploration Agency recently one-upped Near. It's the first spacecraft to ever land on an asteroid and then return to Earth. It arrived in June 2010 after a 4 billion-mile round trip.
As planned, most of the spacecraft burned up in the Earth's atmosphere, but the sample return capsule successfully landed in the outback of Australia.
Even today, it's still unclear if minute samples are present. The careful examination of the capsule is continuing.
It's a long process, but people are optimistic that we're going to get great data out of the first asteroid samples returned to Earth.
To a geochemist, a couple of micrograms of material is plenty to do some detailed chemistry and mineralogy and compositional work.
Even before Hayabusa returned, another asteroid mission was already underway.
3, 2, engine ignition, and liftoff.
After a 2007 launch, the NASA Dawn spacecraft is on its way to 2 of the largest asteroids in the asteroid belt between Mars and Jupiter. Dawn will arrive at 320-mile-wide Vesta in 2011, orbit for a year, then reach 600-mile-wide Ceres in 2015.
You couldn't find 2 asteroids more different from one another. Ceres is thought to be relatively wet, perhaps subsurface ices. And the other one, Vesta, is thought to be the opposite. It's completely lacking in hydrated minerals or water ice. It's been heated over its lifetime to such an extent that it's thought to be layered. A surface layer, a mantle, and a core, much like the Earth.
All of these missions are revealing that asteroids are made from a much wider assortment of materials than we first realized.
There's a huge variety in asteroids. Some of them are iron-rich or nickel-rich, very much like this iron dumbbell. Others are very similar to this earthbound rock. They're stony, they're rocky. Still others are a combination between the iron type and the stony type. We've also got exotic things like rubble piles, which are like having this handful of gravel, but if it all were gravitationally bound in a big asteroid kind of a form. We also have X-comets. And X-comets have gotten rid of all their ices, and we're left with this fine-grained material held in a very porous type fluff ball.
But asteroids are surprising us in other ways besides their composition.
The Galileo mission on its way to Jupiter went past an asteroid called Ida and discovered that it had a little tiny moon called Dactyl. This was a big surprise, and now we see that that's not so rare an incident. Asteroids do come with their own moons, sometimes several moons.
We're also learning that a lot of asteroids are traveling in pairs, as binaries, or even with 3 of them. And that's a very new set of observations and a new thing to understand.
Knowing how asteroids are grouped and what they're made of is more than a matter of scientific interest. Imagine in the future that an enormous, deadly asteroid is speeding towards Earth. It needs to be deflected if mankind is going to survive. But if we don't know exactly what the asteroid is made of, then the effort to save the planet could go horribly wrong. An asteroid impact can unleash more destruction than just about any other kind of natural disaster. But it's also one of the few types of nature's fury that we may be able to prevent. Imagine in the future that a huge asteroid is racing towards Earth at 70,000 miles per hour. International space agencies have banded together and launched a rocket in an effort to save mankind.
The trick is to understand the enemy. Is it made of solid iron? Is it made of shattered rock? Is it made of a rubble pile, an excometary fluff ball? Because if you hit a slab of solid iron with a spacecraft, it's going to react far differently than an object that is a fluff ball.
The asteroid turns out to be a rubble pile. It's soft enough to mostly absorb the impact of the rocket and to stay on course to collide with Earth. It's also large enough that it doesn't burn up in the atmosphere. It hits and forever changes life on our planet. This is the price we could pay if we don't learn as much as possible about the variety of asteroids in our solar system. But at least with large asteroids, we should have years or decades of warning about their approach. With comets, even enormous ones, the warning time will be measured in months. Why? That's what Clayton L. in Atlanta, Georgia, wanted to ask the universe. So he emailed us. Why would there be so much less warning time before an Earth impact for a comet compared to an asteroid?
Good question, Clayton. We'd love to know when something might hit us. It turns out that asteroids are so nearby that we can track their orbits precisely. That means we can make accurate predictions of where they will be, tens or even hundreds of years in advance. That means we might be able to deflect them before they hit the Earth. Now, a comet comes in from the outer depths of the solar system and doesn't become bright enough to see until it's maybe 6 months or a year away from hitting us. So we have very little warning. Fortunately, most of the things that potentially could hit the Earth are asteroids, not comets. And we can track the asteroids pretty accurately.
The fact that asteroids have a much greater chance of destroying life on Earth sometime in the future is one of the main reasons why studying them with unmanned missions is so important. But in April 2010, US President Barack Obama announced an even bigger challenge.
By 2025, we expect new spacecraft designed for long journeys to allow us to begin the first ever crewed missions beyond the moon into deep space. So we'll start by sending astronauts to an asteroid for the first time in history.
In my experience as a college teacher, the younger generations, they want to go beyond. Yeah, my grandparents went to the moon, you know, let's go beyond. And so that was an inspiring part of the president's message, that we need to get NASA back into the business of deep space.
A manned mission to an asteroid will be very different from moon missions of the past. In some ways, it will be easier, and in other ways, much harder. Whichever asteroid the astronauts visit will likely be a lot farther from Earth than the moon. So the journey will probably last for months instead of the 8 days it takes to get to the moon. But the round trip will actually use less fuel than a lunar landing mission.
When you go to the moon, you're dealing with a body with significant gravity of its own. You're having to use more fuel to safely slow yourself down and descend all the way to the surface. When you head to an asteroid with very low gravity, even though you're going farther to get there, you aren't having to expend nearly as much fuel for things like getting to the surface. It also takes less propulsion ability when you leave the asteroid to head back to Earth.
But landing on an asteroid surface will be much more challenging than setting down on the moon.
It's more like docking than it is landing. But you do have some gravity, so you have to deal with having a little bit of gravity. But you have to deal with actually anchoring yourself, holding on. You don't have to hold on when you're in the 1/6 Earth gravity of the moon.
Exploring a small rotating asteroid will also be much harder for astronauts than hopping around on the moon.